In studying linear algebra, we'll be working with matrices a lot. What's a matrix? Well, here's 4 different examples. That top left matrix has 3 rows and 3 columns, so we say it's a 3 by 3 matrix. That's its size. The next one has 4 rows and 2 columns, so it's a 4 by 2 matrix. This one's a 2 by 3 matrix. And the last one is a 4 by 6 matrix. Let's just focus on this 2 by 3 matrix and decompose it into its rows and columns. Here's our rows of that matrix. And there's the 3 columns. We can even talk about each entry or each element. So the number 1 is the 1, 1 element. 10 is the 1, 3 element. And 2 is the 2, 3 element. So this is the kind of language we'll use when describing a matrix. Now, matrices will be used to describe systems of equations. A coefficient matrix is a matrix of just the coefficients for that system. Notice the coefficients on the top equation is 1 and 5, and the coefficients for the bottom equation is -1 and 3. And then if we want all the numbers from that system of equations together in one matrix, we call that the augmented matrix. We augment or add on the last numbers 10 and 2 onto the coefficient matrix, and we call that an augmented matrix. It represents our whole system of equations. Here's another example, 3 equations with 3 variables. Here's the coefficient matrix in the augmented matrix. Let's look at solving this system of 2 equations. Now, to solve a system means we want to find 2 numbers that when we plug those numbers into x1 and x2, it solves both equations simultaneously. So that's what we're looking for. You could try guessing 2 numbers and plug them in, but chances are if you just guess, it won't solve both simultaneously. So we need to come up with a method to solve a system. You may already encountered 2 equations and 2 unknowns in other courses. Maybe you solve for one variable in terms of the others and then substitute the other equation. That process can get pretty messy when you're dealing with bigger systems. So we're going to just work with what we call the elimination procedure. And our first step here would be replacing equation 2 with the sum of the 2 equations. Notice when I add equation 1 and equation 2 together, the x1 disappears, right? Because we have x1 plus negative x1. So we eliminate an x1, and we're going to call that our new equation 2. And so we get this new system of equations here. And this new simpler system still has the same solution as the original system, right? Because I haven't affected what our solution would be. One way to think about it is when I add equation 1 and 2 together to make that my new equation 2, you can think about it as adding 10 to both sides of the equation 2. Right? When I add them together, I do 10 plus 2 is 12. You can think about adding 10 to the left-hand side too, but we know 10 is just equal to x1 plus x2. So on the left side, instead of adding 10, I add what is equal to that 10, which is x1 plus x2. So that's a valid operation to do. It's just like adding 10 to both sides. I don't change the solution, but I've simplified our system. Next, I'm going to scale the second equation by 1/4. Right, so that simplifies my system a little bit. Right away, I know x2 is equal to 3 now. Next thing I'll do is I'm going to change equation 1 by scaling equation 2 by -1 and then adding it to equation 1. Because then I'd have negative x2 plus x2. That eliminate the x2 in the top equation. And I have negative 3 plus 10 is 7. So my top equation is simplified. And from here, I can actually see my solution is 7 and 3. Now, what we'll end up doing more in the future is representing these systems of equations with matrices. Because when we have all these variable names, like x1, x2, it's messier than it needs to be. Right? We really don't need all the x1 and x2s in there. We could just use a matrix like that and just know that the first column corresponds to the coefficients of x1, and the second column corresponds to the coefficients of x2. Then we can do all the same math we just did and not worry about writing our variable names down every single time. So this last matrix is telling us x1 is equal to 7 and x2 is equal to 3. Let's verify that this is true. I look at my original system of equations, and then I replace x1 and x2 with 7 and 3. And yep, that does satisfy that system because 7 plus 3 is 10, negative 7 plus 9 is 2. So we have actually found the solution to the system. We can think about what is happening with this system visually by graphing our two equations. I'm in Desmos here, and Desmos doesn't like the variable names x1 and x2, so I'm going to use x and y. So our first equation would be x plus y is equal to 10, and the second equation would be negative x plus 3y is equal to 2. And we see these two lines, right? These are equations of lines. And where they intersect, that is the solution to our system of equations, because the intersection means they share the same point. The same point is on both lines. The point solves both equations at the same time simultaneously. It's where the two lines intersect. So we saw that the point was 7, 3. Right? So there is our solution to the system. Let's look at a more difficult example. Here we have 3 equations and 3 unknowns, and we're looking for a solution to this system, which means we're looking for 3 numbers such that when we plug them in to x1, x2, and x3, it solves the 3 equations simultaneously. Here's our augmented matrix. Eventually we'll just work with matrices because it's simpler to write down and to look at. But for now, we'll look at both since matrices are new. We'll see them both working at the same time. And to start solving this system, we want to eliminate x1 from the second equation again. And we'll also eliminate it from the third equation. And the 2 operations that would do that is we'll replace equation 2 with negative equation 1 plus equation 2. Right? Notice you'd have a negative x1 plus x1, so that'd become the new thing in equation 2. You'd have 0x1. But then you also have to work with the rest of the variables. Right? You'd have negative x2 plus 2x2 and negative 3x3 plus 4x3. And you also have a negative 8 plus 12. That'd become the new equation 2. And again, why does that work? This is a good thing to think about. Why are we allowed to do that? Why doesn't that change the solution to the system when we manipulate equation 2 like that? Well, you can think about it as I'm just adding negative 8 to both sides of equation 2. I'm doing 12 plus negative 8. I'm also adding negative 8 on the left-hand side of the equation. But I know negative 8 is equal to negative x1 plus negative x2 minus 3x3. Right? So I'm just adding the same thing to both sides. I'm not changing the solution to the system. And for equation 3, if I do negative 2 equation 1 plus equation 3, I'll also eliminate that x1 from the third equation. So this is the new system we get in the corresponding augmented matrix. All right. So maybe it'd be a good spot to pause the video and just study why that is the new system. And notice it's a simpler system because I've eliminated x1 in equation 2 and 3. All right, next I want to eliminate the x2 from the third equation. And to do that, all I have to do is replace equation 3 with the sum of equation 2 and 3. Because then I have x2 minus x2 would get rid of the x2. I also have an x3 plus 0x3 and a 4 plus negative 1. So my new third equation is just x3 is equal to 3 and my corresponding augmented matrix. Notice my augmented matrix has this diagonal of 1s, which we'll see later on is what we really want to work towards. And we'll notice that as a pattern. All right, we haven't actually solved the system yet. All we've figured out is x3 is 3. But what is x1 and x2 equal to? Well, we can keep doing these operations to eliminate x3 from equation 1 and equation 2. So notice if we do a negative 3 times equation 3 plus equation 1, we'll eliminate x3 from equation 1. And likewise for equation 2, if we do negative equation 3 plus equation 2, we'll eliminate x3 from equation 2. So we'd get this new system of equations that's getting simpler and simpler, right? And the augmented matrix that represents it. So another good spot to stop and just study what happened from one system to the next, right? And all these systems have the same solution, right? Because we're essentially just adding the same thing to both sides of all of these equations. So we're not manipulating the system in a way that changes the solution. We're manipulating them in a way that keeps the same solution, but we're getting eventually to the simplest possible system so we can just read off the solution eventually from the system. All right, so we're almost there. We still have an x2 in the top equation, so we're going to eliminate x2 from the top equation by using equation 2. Right? If we do negative equation 2 plus equation 1, so there it is written down, we'll eliminate equation, x2 from equation 1. And notice that negative 1 also turns to negative 2 because you have a negative 1 plus a negative 1 is negative 2. All right, so there is our augmented matrix in its most reduced form, in its simplest form, where we can read off the solution right away. That matrix is telling us x1 is equal to negative 2, x2 is equal to 1, and x3 is equal to 3. Now let's verify. Right? This is always a thing you can do when you think you have a solution. Let's just verify that it actually solves the system. So we take our original system and plug in our numbers, negative 2, 1, and 3. And there we go. And you can add those up and make sure, yes, that does verify. That does solve all three equations simultaneously. Again, we can think about the system of equations visually, this time in 3 dimensions. Each of these 3 equations describes a plane in 3D space. So the first equation is shown in red. And there's the next equation and the next equation, right? So we have 3 planes, and this time the solution is the spot where all 3 intersect. And we found that was the point negative 2, 1, 3. So x equals negative 2, y equals 1, and z is equal to 3. That's the orange point there. Now it would be hard to kind of identify that without me plotting the point. But I'll give it a little spin here so it's easier to see. Right, those 3 planes all intersect at negative 2, 1, 3. So that's a way to think about it visually. Now that we've gone through 2 examples of solving system of equations using this elimination procedure, you might see this pattern. If we look at this bottom augmented matrix, there's 1s on the diagonal. So maybe these operations to simplify this system of equations seemed a little arbitrary, but if we have this goal of getting the 1s in the diagonal, it'll help direct our steps. And so the more we get practice with this and try to get these 1s in the diagonal, so that we can read the solution off from this matrix right away, because this matrix just tells us what our solution is, right? It says x1 is equal to negative 2, x2 is equal to 1, and x3 is equal to 3. Knowing that kind of form there with the 1s on the diagonal, that will help us and guide our steps on when we're trying to eliminate certain variables from certain equations. All right, we'll see more of that in the future, and we'll also see that it's not always possible to get 1s on the diagonal. And we'll see more of that later too. All right, that's it for this video. Thank you.